Okay, good morning or afternoon or whatever, everybody. Let's recap what we've got going on. We've been working on particles, and we added all these particle features so far. Um, we've got a pretty good basic set of features now. The only thing we don't really have is good control over changing color over time, which is something that I want to discuss with some people on the team to figure out what the best way is to do it. And it's probably going to involve programming some substantial UI for that. In the previous stream, we did particle stretch as one of our features. And what else did we do? We made drag frame rate independent. And then we started working on the UI for these random variables. Specifically, when I click on them and, I can see a little visualization of what this thing, the distribution is for these numbers. However, it's a really crappy visualization with some bitmaps that I just scribbled. And the gamma is also wrong, which makes it even worse. But, you can see that these aren't very carefully drawn graphs. And they may not even be right. So I was thinking about this. So each of these routines here, the way these happen is, there's just a little snippet of code that happens for each one of these, right? Now, I was thinking that because I haven't actually done the math on what some of these things are, that some of these shapes may not be as interesting as we want them to. So like 3 dice squared versus 4 dice squared, like those may not be different enough to care. And like maybe we get a better shape if we square these terms and then normalize, etc. So that is the situation. And then what we were talking about last night, I also spent some time being confused about probability, which is good because it's about learning. And what we were saying last night was, this is a computer and computers are fast. Instead of drawing a bitmap here, the funny thing is we're drawing this name like x cubed and then this routine, and this doesn't look like y equals x cubed because it's not. It's like the resulting probability. So maybe we don't want to call this like x cubed because maybe that's just confusing. You know what I'm saying? So maybe we just come up with different names for all these. But first, hey, computers are fast. So instead of having these bitmaps, which sort of live here, no, it's in here. Why don't we just live graph this thing? And then we might even do some stupid UI thing where it animates into place. Wouldn't that be fun? And then we can actually see what our distributions are and so forth. And I will have to think enough about what these functions actually are, right? So this is x squared. This x squared just means what I'm doing to the, we generate a random variable with uniform distribution from an LCG, pseudo-random number generator, like you would expect if you program, right? It's very fast to do that. And we say that's a float between 0 and 1, and then we square that, which gives you, y equals x squared. But then the inverse function of that is this thing called the cumulative distribution function, I think, right? And then the actual probability graph, as you're used to seeing it, is the derivative of that cumulative distribution function, right? So this is the derivative of the inverse function of this. And I think that's the thing to visualize to show the actual shape. Anyway, so I think we're just going to live graph it and have a party now. Can I dedicate a thread that will run Monte Carlo trials in the infinity loop and fill the graph in like 10K bitmap, and then you'll downscale it and use in button. That way, the longer the application runs, the more precise the image becomes. Like ray tracing and stuff. Why stop there? Why not ray trace it? Like, why not have machine learning learn what the shape should be, and then you draw what it thinks the shape is? Why don't we do all these things? Okay. So let's just start typing things. What I want to do is I want to make the graphing logic first. And we'll just insert some kind of dummy function for all of these. And then we'll fill it out. Right? Right. Okay. So we're going to have, we're going to delete these texture names eventually. But we're going to have some graphs that we initialize. So we're going to say RV graphs. It's an array. The length of the array is RV nice names.count, because there's one for each of these. And we're just going to have a subarray in there of float. Well, let's say num graph samples is 100. I don't know. Okay. That way we don't have to dynamically allocate anything. Right? Okay. So init graphs, and we're going to have a graphs initted. Okay, whatever. So let's just fill out all of these graphs with just stupid things for now. Okay, so we're going to take a pointer. No, well, let's just go by index. Let's call this, oh, I don't know, sample index. Okay. So we're going to do that. And we're just going to generate the math for each sample. You know what? Let's just go ahead. Okay, so no, you know what? It's going to be easier to think about this if we just do it one at a time. what are these actually called? Using probability control. That's the enum. So uniform we're sort of picking an arbitrary y value for this to look good. We just want it to be a horizontal line. So RV graphs sub uniform sub sample index equals uniform scale. Okay, that's fine. And you know what? We're just going to go ahead and do the right things here. So x is, so let's say dx is 1.0 divided by right? So if you have 100 numbers, you have 99 intervals between the numbers, right? So maybe this loop is going to be cumbersome enough that we want to do it the other way around. Let's see. So x0 is sample index times dx. x1, oh, actually, we don't need that. Let's just say x, right? So if x, what we're graphing here is derivative of inverse function of y equals x squared, right? So, right, so x squared, its inverse function is square root of x, right, or x to the 1/2. So the derivative of that is 1/2 x to the minus 1/2, right? Now, x to the minus 1/2 if x equals 0, what is that? I don't know. Let's just make a constant for infinity that's going to be off the scale of the graph. So y is high, right? Otherwise, y equals times pow x minus 0.5. We're not going to be lazy and refactor that, right? Y, and then we're going to leave that unscaled, all right? See, this is enough boilerplate. Oh, this is not uniform anymore. This is x squared. You know what? Let's just do all three of these at... Yeah. I don't know, man. I keep changing my mind about how to do this. So, right, so that's going to be x cubed, and x to the 4th is going to be 2.5 pow minus 0.25, right? And those are going to be the only ones we do so far. We'll figure out the math on some of these other ones later. The rest of our graphs are going to be 0. Actually, let's put some data there. we'll just make all of the rest of them be level, right? So, and this will also serve as our to-do list of what we have to implement. 1 minus x cubed, 1 minus x to the 4th, 2 dice, whoops, 3, oh, come on, I thought I copied that. 3 dice, I didn't, obviously. 4 dice, 2 dice squared, 3 dice squared, and extremes. Okay. Let's see if that compiles. It probably won't. Oh, look, it did. So, okay, we're not ever calling this. We're just going to call it down here. I don't know. Actually, let's call it up there. And let's make sure we don't like divide by 0 and kill ourselves or something. Our visuals will not be any different because we're not using any of these numbers. But we did call init graphs, as far as I know. Okay. Now, instead of drawing a bitmap, which we're doing here, let's just do it. Let's just butcher this. RV texture names gone. We're just going to get the nice name out of this routine. Okay. So map name is gone. And but we're still going to do all this stuff, the image X, image Y, all that. So instead of saying draw textured quad clipped, we're going to say draw probability graph at image X, image Y with width, and we're not even going to pass color right now. Okay? So, oh, and we need to know which graph it is. Index. Graph index. Okay, which means we need to go back down to this thing and return graph index, which is an int, and comma I64. All right. So draw a probability graph. Let's call these x0 and y0. And this is just not going to do anything yet. And let's make this ensure graphs are knitted down here because, you know. And, whoops, RV texture names. I deleted the wrong one. This is RV nice names. Okay. So now we're just not going to draw anything. So we're worse. This is the worst the program has ever been in history. All right, yeah, now we just got an empty space there. But now we start to do the work. Okay, so all right, so here we're going to have a dx, which is w times 1.0, w times this, or just w divided by this, really. Right? So this is dx in screen space, and we're going to go for, now we're going to say x0 is I times dx, x1 is I plus 1 times dx, right? We're going to say y0 is actually minus 2, because we're going to draw quads. So y0 is rv graphs graph index sub x0, and y1 y0. These aren't 0 and 1 in terms of min and max. They're like just neighboring. Maybe I should call them a and b or something. X1, sorry. All right. And, well, so we set the shader here. Let's say color. Let's just draw in white to start with. And right, so we're going to call this version of immediate quad. So immediate quad, well, let's just paste that, right? And we'll do an immediate begin and flush. Even though it's really redundant, it's probably good style to do that. So, well, what are P0, P1, P2, and P3? Well, P0 is going to be a vector 3 of x0, whoops, haha, corner, let's call this corner x, corner y. Because we're calling these 0 and 1, it's like, So x0 is going to be corner x plus corner x plus. This is a little bit messy because we're sort of changing the meaning of y0 and y1 here. Corner y plus y1 times w. Okay. x0, y0, 0. P0, 1, 2, and 3. X0, y0, x1, y0, x1, y1, x0, y1. So that's just going to be a quad, and we're going to draw that. Array subscript must be an integer. Ha ha. What kind of a dummy am I? Okay. It doesn't like our overload of immediate quad. Oh, we have one for vector 2s with color. Let's use that. Okay, question is, do we get something on the screen? Now notice, so we're not scissoring this, so the graph can go out of bounds, which is going to be entertaining. Well, we don't see frickin' anything. Why not? Oh, we see a little bit. I think it's because we have a texture map active. So let's just do this. because we might want to assign a texture map later to like give a little bit of texture to the graph. But in fact, that would be hilarious. Well, still no. Oh, there we go. Okay. One thing that we're doing is we're actually, yeah, we're graphing the thin line at the top here. What are we doing for uniform? So uniform, somehow the scale is not good. I don't know what's going on there. Or the values aren't good. X squared looks correct. Except that we're kind of going to the right of where we should. That's kind of weird. Okay, so we have a couple things. So let's make our graph a little more sophisticated. We're going to do a foreground color and a background color. The background color is going to be like a cyan-ish. We'll tweak that later. We're going to put these in a tweak file probably. And so we're going to do the background first, and then the foreground. And the background is just going to be corner Y instead of Y0. Right. Oh. There we go. That looks a little bit better. So I'm doing this weird thing. The quad that I drew for the top line is not really what I want to draw. See how it's like changing in thickness? So really we want to do something else there. We want to like draw line segments along the top. Any questions about what's going on so far, by the way? So the reason it doesn't appear for uniform actually is because you know, because two things are at the same height, the line thickness is ending up to be 0. Right? Because the y values are the same and the x values are just further to the right. So we have the reason this was invisible before we drew the background was we had lines of no thickness. So I kind of want to scale this a little bit. I mean, I'm not really sure what the right answer is for that. Like the area under that curve is not 1. So I kind of think I want to normalize it. Dude, I don't know. should I plus 1 times dx be I plus 1 times dx? Yes, it should. Wait. If that wasn't right, let's just do this. Like, wait, how did that do anything? Corner x plus I plus... Okay, well that's another... Okay. That's really weird. How did we ever... Oh, because we have so many samples. Our x1 was wrong every time, but because we had so many samples, we couldn't really see it because they were splatting on top of each other. Yeah, okay. So that's a little bit less messy, but it still has the same problem. Like, we haven't actually really solved the problem. So here's what we're going to do. We're going to say top line width. Let's say top W is W times, I don't know, 1/30th. Let's just do a divide. Who are we kidding? Okay. So here's what we actually want to do here's the background. And then for the foreground, we want to say, okay, let's call it A0 is some vector from x0 and y1, and A1 is some vector x1 and y1. So this is the vector along the top of the graph, right? And then the direction is A1 minus A0 unit vector, right? So that gives us a unit vector that points along the direction of whatever that thing is in the top of the graph. And then the perpendicular is going to be something that goes in the orthogonal direction of that direction, which you can do just by twiddling the components like this. So now this gives us a quad. Now, we might accidentally draw this back facing, in which case yeah. So in the way that I tend to, in which case we just flip the sign. And the way that I tend to think about this is I tend to make a thing called strut, which is just the delta from a point in the middle out to the edge. That's just perp times top W times a half. Because you go out halfway, you go, you'll see. So P0 is going to be A0 minus strut. P1 is going to be A1 minus strut. P2 is going to be A1 plus strut. And P3 is going to be A0 plus strut. So we're just going around. So hopefully that'll give us a constant width. Top line, it may be too thin, I don't know. I may have totally screwed it up and we may delete every computer program on the internet. Nope, there we go. Well, that doesn't really look right. I think we messed something up. Because it doesn't look right. This should be a good line. So let's hack this. Let's just make it a diagonal from 0 to 1 every time, and we'll just redraw the same thing over and over. Oh. So we're just going to do that. Oh wait, I did that on the background. That's the wrong place to do that. We want to do that here. So we're making it big, and let's just see what we screwed up. Why am I drawing it horizontal all the time? I thought I was going to be diagonal. Oh. Oh. Yeah, this is stupid. This is supposed to be y0. Right? I kept getting confused. I said y1 because it's the top of the graph, but y is always the top of the graph. It's just this is sample index 0 and sample index 1. Okay, that's what I screwed up. At least. I may have screwed up other things as well, but that is definitely a thing that I screwed up. Okay, that looks better. That looks like I expected. It's not really anti-aliased, unfortunately. We may have to turn on some anti-aliasing. Okay. Okay. Let's scissor these so that we don't get this ridiculous out of bounds thing. Any questions about what's going on? Seems like eye tracking is off. Look, man, I just work here. Oh, it's off. Dude, it just fails all the time. Like, you have to unplug it and replug it. No, it's still dead. I don't know what to tell you. It's a computer in the year 2018. Software just can't function correctly. Right. Oh, wait. No, it's... The tracker is on now. It's just... Oh, this report is very... Wait. It's confused about whether it's on or not. It's failing and unfailing. Dude, my device may just be failing here because... or maybe I just need to sit further back now. Just if they would angle this damn eye tracker up a little bit. It's got this mount thing, and it expects me to be sitting like back here, which is stupid. I'm not going to sit back here, but like that's the angle of the mount that they put. So it's always this like awkward situation. Like it's not tracking me right now. God, I'm ready to throw this thing out the window. Like if I just rotate it up a little bit. Okay. Here's what we're going to do. We're going to put some tape behind the eye tracker to try to angle it forward. So it's got this like magnetic mount. So we're just going to see if this helps. Such a disaster. Like it's a cool idea and they just fucked it up. Like, I don't know. All right. Okay, we'll see if that helps. All right. How expensive was the eye tracker? I don't know. You could look it up on Amazon. I don't remember. What are my computer specs? It's a PC computer machine. Okay. Am I going to move the graph to its own section, or is drawing over stuff fine? Well, we want it where it is. We want it where it is. We just don't want it to draw out of bounds. So we're going to scissor it. All right. I just don't remember what my scissor routine is called. Oh, set scissor and clear scissor. So at the start of draw probability graph, we're going to call set scissor to corner X, corner Y, W, W. And down here, we're going to say clear scissor. All right. Nope. We're just going to cast this for now. Okay. There we go. We're scissoring. Okay, so let's do some more of these graphs now. Right? So 1 minus x squared cubed and to the fourth. Actually, that's not going to be right. Hold on. So we're doing to the interval, right? Y equals 1 minus x squared. So to inverse the function, we solve for x in terms of y. So y equals 1 minus x squared. We subtract 1 from both sides. So we say y minus 1 equals minus x squared, right? So 1 minus y equals x squared. X is square root of 1 minus y, right? That's the inverse function of that. And the derivative of that is, of course, 1/2 times 1 minus y to the minus 1/2. So it's, it's basically the same thing, but with a 1 minus where you would want it. So okay. 1 minus x squared, 1 minus x cubed, and 1 minus x to the fourth. Question is, do we really even need these distributions? I don't actually know. We're sort of skipping 0. Oh, no, we're not, because it's, yeah. uniform, x squared, x cubed, x cubed, 1 minus x squared. Yeah, so it's just the flip of the other thing, which frankly you can do by exchanging these values. So I'm not sure it's worth having these, honestly. Maybe it is. I don't know. Okay. So now the hard ones, I don't know what 2 dice, 3 dice, and 4 dice squared are supposed to look like. Maybe we'll build histograms of those. Yeah, you know what? Because we're being insane today, let's do this. So for 2 dice, we're going to do a histogram. I mean, I know what the analytical solution is for 2 dice. 3 dice and 4 dice, I would probably fudge with Gaussians. Yeah, okay, so instead of setting this up here, okay. We're going to say hits is what is it called? Num graph samples int, right? And then we're going to say 10,000. We're going to say for 1 to num hits x0, or no, let's say xa is random get, is it 0 to 1? Yeah. I'm going to say xa is that, and xb. Right, and then do we have dx in this scope? Yeah. So we're going to say the index is x divided by dx casted to like right, and then hits sub I plus equals 1. Okay, so we're doing this function, and we're going to factor this out later when we end up calling it more than once, but for now we're just doing this. So we're Monte Carlo simulating, and then so we want to find the max and then scale. So for so we're going to say highest is 0, right? If hits I Actually, we can just say for hits if it is greater than highest, highest equals it, right? That'll give us the highest value in the array. And then we want to scale it. So we want to say scale equals, we're going to use, I don't know, 0.95, not quite 1, to give ourselves some room for that, you know, thick line. I don't know. This is going to be a little bit of a fudge, but it's fine. Scale is 0.95 times actually, let's say scale is 1.0 if highest. If we somehow have 0, we don't want to divide by 0. Otherwise, right? So highest will map to 0.95, and anything proportionally less than highest will map to less. And then 2 dice sub sample index equals scale times hits sample index, right? There's our histogrammification. Oh. Clamp, we take a pointer to I. Array subscript must be an integer. Oh, geez. Precedence of cast, man. Okay. So there we go. Oh, we're doing it every frame. How wonderful is that? That's like some indie glitch aesthetic crap right there. So for 2 dice, yeah, I don't know. Does Unity do this? I don't think so. All right, so now, so what's bothering me is that we're not supposed to be calling init graphs every frame. Oh, because of this. It's cooler when we do it every frame, so maybe we'll turn that back on. But let's just do the rest of these. So we're going to say, so we're going to go here. Just so that we can reuse this hits array. And we're going to factor this out, right? We're going to say it's going to get slower because we don't have macros that'll do this yet, but we'll just make a lambda. So we're going to say histogram into RV graphs sub 2 dice scale of 0.95 and x goes to, well, just do this, right? And then we'll say 2 dice is we're going to do that. All right. So then we're going to say histogram. Destination is an array of num graph samples of float, right? And scale is a float, and the function is something that returns a float. Actually, we don't need to clear this if it's a local variable. Y equals func. Well, let's just call it X there. Let's call this Y scale. No. Y scale. And then this is dest there. Dx. We'll just recompute that here so we don't have to pass it. Did that work? Chook, chook, chook. 2 dice. All right. So we now easily can do 3 dice and 4 dice, right? So 2 dice, 3 dice, 4 dice, right? See what I'm saying? Okay. Per particle. 2 dice, 3 dice, 4 dice. Not that much difference between 3 dice and 4 dice. Okay, so 2 dice squared, 3 dice squared, and 4 dice squared are easy. I'm not really sure, like I said, if these are worth it. Let's see. This is freaking stupid. What am I programming in Lisp? Oh, you know what? I don't think we have a quick lambda for no parameters. These are all procedures of no parameters. Maybe we do. Hold on. Right. So this is, dude, I don't know. I don't know if I made this syntax work. We're just slinging out code here. Well, maybe I did. Okay. Boom. Per particle. 2 dice, 3 dice, 4 dice, 2 dice squared, 3 dice squared, 4 dice squared. Pretty good. Extremes. That's the only one that we have to do. This is good too because it's science, right? Like if I mess up my math, we have empirical confirmation of what these things should look like. Okay, so extremes. I don't even remember what that is. Now, to be especially good, we would define these somewhere common and then inline them from here so that we're sure they're the same functions. But for now, we're not going to do that. What did that complain about? Not all control paths return a value. All right. That's pretty extreme. So we get to declare victory already, and it's only an hour in. I feel like we should do something cool. Either we could leave these animating every frame. Like we could just have all of these be histograms, like noisy histograms and animate. I'm going to do them. That's stupid. Okay, so first of all, let's do a little bit of stuff before we get stupid. Let's just look at how good were my doodles, right? Like, okay, x squared. X squared we knew because we graphed it, right? And I sort of like tailed it off here, but you know, for drawing in Photoshop, not terrible. X cubed, you know, x to the fourth. Where's my x to the fourth? Yeah, you know, 1 minus x squared. I think I had the wrong idea about what these are. Like, I did 1 minus here, which is not the right thing. So these ones were not right. 2 dice I knew analytically. 3 dice, I probably made a little bit fatter than it is. And 4 dice, I also, 2 dice squared, I probably didn't square it hard enough. 2 dice squared, oh yeah, dude. Oh, my 2 dice squared is pretty far off. 3 dice squared, not so bad for someone who just like guessed what it is and drew a line. That's not the worst. 4 dice squared is really not that different from 3 dice squared. I don't know. I mean, if you're actually generating particles, maybe it's different. 4 dice squared. It's really not that bad. Extremes. My extremes, I thought the middle was a lot higher and these were a lot wider than it actually is. That confuses me though, because this is essentially just 2x squareds, but like, how is x squared so broad, but extremes? See, I don't know about that. This one is weird to me. I don't understand why extremes is so extreme, but that's fine. It is. It's science. So now we delete all this stuff that we painstakingly, anyone who saw the stream last night knows how annoying it was to make all those bitmaps. And we say graph distributions in a more accurate way. All right. So now we're going to be super stupid. We're going to be so stupid, it's amazing. So we're not... Okay, before we get super, super stupid, we're going to get moderately stupid. And even for stuff like uniform, we're going to comment all that code out that we just worked so hard to do. And we're just going to make it all using this histogram system, right? You know what's interesting is this also serves as a test of the random number generator system. Because when we return uniform, like we want to see a flat line, and if it's not, that actually tells us if our random number generation is wrong, right? So uniform is just, x to the first. Okay. So we're going to histogram. Actually, let's... What am I doing? Okay. Uniform x squared, x cubed, x fourth, Okay. Okay. So uniform. It's kind of uniform. X squared, x cubed, x. Wait, why are my x squared so extreme now? The math must have been wrong. Huh. The math that we did was wrong. That's why extremes was so much more extreme. Actually, maybe the math was right, and it's just our scaling was not good. Like we had to zoom out for some reason. Because this is. Oh right. Oh right. Yeah. We are zoomed out. That's all. We're zoomed out because we're like taking the max, right? So how do we alleviate that? Let's pass in see, the problem is if we threshold on the maximum value is going to be noisy. You know what I'm saying? We're going to say ignore left equals 3. We're going to say 1/10 on either side. Let's just, yeah. In our histogram routine, ignore stuff at the margins so that our scale does not get crazy. Incomplete. Maybe we want to adjust this better per function, as we might have stuff like mid-extreme that peaks in the middle. So we're just going to let things go off the graph, and ignore is going to be num graph samples divided by 10. So the left 10th and right 10th of the domain are going to just be allowed to go off the graph. All right. Uniform x squared. There we go. There we go. Much better. Much better. See, now my doodles were not even that bad. Remember my doodle for extremes? Yeah. Yeah, baby. Okay. I know math. Okay. So now is when we get, okay, let's check this in. Now is when we get truly stupid. Okay. So we're not going to do this ensure graphs a knitted thing. And Actually, no, let's do one more intermediate step. So instead of doing all this, we're going to put these functions here, like here. I'm going to sure hope this is file scoped, because here's a mess of stuff. Will that compile file scoped? Yeah. Okay, so instead of doing this big series of things, we're just going to say for okay, let's delete all this code. Okay. So we're going to go for, well, low to high. Sure, why not? We're going to say f is rv graph procs of it, right? And then histogram f 0.9, or sorry, rv graphs it f 0.9, other order of arguments, right? So we're just going to have rv graph funcs, rv graph funcs, oh God. I don't actually have a way of doing this yet. Yeah, we do. We're just going to do this for now. Would like to just put the procedure literals here, but we don't have a way to do this with our current array literal syntax. Sad. Okay, we're just making an array of these routines, and we're just going to initialize it here. So we're going to whoops. And then okay, I guess my replace didn't quite work here. I don't know why. What the hell is Emacs doing to me? What is it doing? I'm just trying to copy this region. Okay. Dude, I don't, okay, whatever. I'm just going to do the rest of this by hand. Oh, we have a different number of spaces, and that's throwing it on some of these. Let's just stop being fancy here. Okay, we shouldn't have had to do this in the first place. It's fine. This is the penalty we pay for not having totally made everything in our programming language as good as it should be. Okay, so 2 dice squared. Right, and then 3 and 4. Okay. So we'll put those next to the other dice routines. Okay. Does that work? Oh, we're not using our thing anymore. We are. It's just too low down in the procedure. RV graph procs. It's funcs. Oh, and wait, what? Dude, I am brain dead. I don't know what I'm doing. Okay, so this should not really be any different. All we did was refactor some things. Uniform, x squared, x is... yeah, okay. Okay, this is fine. This is all good. This is exactly what we wanted. And now is when we get stupid. The whole reason we did this was just so we can get stupid, right? Okay. So to draw the probability graph, we're just going to redo whichever one is the active one every frame. So we ensure graphs are knitted, which now just pokes those function pointers, right? And instead of having this RV graphs at all, we're just going to say graph is num graph samples float equals da 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 da, and graph index, and then we histogram into graph with F, and then there we go. We are now fully stupid, and I like it. Of course, this is going to be frame rate dependent. Okay, now we could denoise this a little bit. I mean, this is already pretty great. I don't know why we're going down on our last sample. Like, I feel like we have an error in our last thing. We could debug that, but I'm just going to write that down. Can you right-click in the editor thing to scroll the other way through the options? Not yet, but you should be able to, right? So I guess I'll do that. Because it is tedious when there are this many. Like, eventually, it'll probably be you click on the image and you get, like, a palette of them. Although, then maybe we're going to be stupidly updating all the histograms every frame. This might be a little noisy. So let's try something extra stupid. So we're going to say last graph index is -1, and last graph num graph samples float. So if last graph index is equal to graph index, right? Else, so if we just switched graphs or something, then we assign this, and I could do a mem copy here, but I'm just going to dumb copy it, like last graph. Actually, why don't we just say last graph equals graph? I think that works, right? It should. Maybe it doesn't. We'll see. Otherwise, for so we're just going to interpolate halfway between. I don't know. We could denoise in a frame rate independent way or something. It's less noisy. We could actually put more inertia on the previous graph, like oops, not O. I mean, the thing is, this hides the random number generator quality question. That's so weird that we're getting the same spikes? Really? I don't know if I believe that. Maybe I do. Now I'm worried. Oh no, we're never changing last graph. Duh. Duh, bro. That's whatever our first roll came out. And that's also why the previous thing with the even weighting didn't look good. So easy to make mistakes in programs. All right. There we go. How's that, man? You even get a little bit of reactivity because the initial randomness is a little higher. It's just, you know, it's frame rate dependent right now, but this is kind of stupid. Like, I like it. Does Unity do this, people? I ask you, does Unity do this? Okay, so now what we got to do is to be frame rate independent. So we're going to get our DT, and if you saw the previous stream, you saw what we were doing when we were simulating drag, right? Basically, we come up with a scalar coefficient where we take a number to the power of dt times a constant, and that gives us frame rate independence. And if that doesn't make any sense to you, which it probably doesn't, if you haven't seen this idea before, you can watch the previous stream, because at the beginning or somewhere toward the first half, I go through the math. All right, so 100 frames a second. Let's just say 60 is our default if we don't somehow get an entity manager. Okay, and then lerp factor is going to be I don't know. This is kind of arbitrary. We're just going to tune this number, right? And then down here we do lerp factor. So now we're frame rate independent. I mean, not exactly, because we're rolling more random numbers every frame. So we're not totally, we're more frame rate independent somehow, maybe. I don't know. It looks like our lerp factor is not high enough. Actually, I think I just want to do that. Come on, bruh. I think we could do with a little more noise than that. Okay. 1. That might be not enough. And all of this we could put in tweak variables or whatever. Wait, what? Oh, right. So right. I was thinking my coefficient is wrong, right? So this is the direction we want to go, obviously. Getting tired, and it's time to go to work, which is okay. So now that's tunable. We just put different constants in there. I don't know, it feels good. Any questions about what we did today? It's weird that 2 dice squared gives us a kind of a level plateau here. Oh no, that's okay. No, that's really a level plateau, because when we go off the graph, the line goes off the graph. So that's kind of interesting. Like, how'd we get that? It must not be really quite slope 0. Okay. Let's try one more thing. Well, let's check this in. Graphs are more fun. Let's make the histogram 10 times as noisy and see what happens. Like, maybe that just means we use a bigger lerp factor. This might be way too noisy. I don't know. It's a little too noisy for my taste. At some point, the amount of motion is just distracting, you know? Oh wait, I went the wrong way. I keep getting confused about which direction that goes. What am I doing at work compared to at home? I don't know. Same kinds of things. Maybe I save the more fun stuff to stream. I mean, I'm probably going to be going through my to-do list and so the x squared, x cubed, and x to the fourth don't look that different to me. X squared, x cubed, x fourth. X fourth and x cubed really don't look that different. But that might be partially scaling factor. But yeah, I don't know. Maybe we take out x to the fourth. Or maybe we take out x cubed. This is pretty sweet. We got to fix this thing on the right-hand side. It's weird. That's probably our histogramming. Oh, you know what? When we histogram, when we divide, we probably want to add 0.5 to round to nearest. Is that right? No, because they're integer buckets. I don't know. I need to think about this. Anyway. Did I take an IQ test when I was a kid? Yeah, I did. Can I just call in sick and stay and entertain the masses? I could, but I'm really tired right now. Streaming makes me tired. I don't know why. Maybe I'll build up more streaming endurance over time. And, you know, I streamed many hours last night, or 4 hours. What is the biggest difference of software engineering compared to other engineering disciplines? Software engineering is the most superstitious engineering discipline.